switch off, you'll be able to see really. Yes, good morning to you, my students. I want to apologize that I'm a bit late, but I hope you're able to see. Confirm that you're able to see. I want us to continue with the concept of refraction that we had started on. Confirm with the concept, continue with the concept of refraction. Now we looked at real depth in our last interaction last week, and I want us to add on by looking at critical angle, and the total internal refraction. Today is the 8th of June. I want to begin by announcing that our YouTube page is called the channel. YouTube channel is now up and running. You can search for Teacher, T-I-C-H-A, Teacher Kakuru D Dwabinomi. But at the same time, I sent you the link. Subscribe, share, and like. And this does not disable our Facebook page of Let's Learn from Home, but the YouTube channel has many videos, and I continue to upload as many videos as possible, including the Let's Learn from Home videos. I'll be uploading each of them at least regularly until I finish all the old archived lessons. So today we are looking at these important terms: critical angle and total internal reflection, and the associated calculations. I request that you should have your calculator nearby, as usual, because we are going to carry out some calculations, and you definitely will need to sample them out. When we are describing these terms, we consider use of several diagrams. And we do it in respect with the physics behind refraction of light. We shall use specifically 3 diagrams, sketch diagrams for that matter. We know that light must, there are conditions we shall eventually talk about, but light must move from a dense to a less dense. So we shall consider motion of light from glass to air for case A. This light will be reflected, this will be a weak reflected ray, and it will be refracted with a strong refracted ray. This one is supposed to be strong. This angle, as usual, is the angle of incidence, and this angle is the angle of refraction. And since there is refraction here, this angle will also be equal. It is in agreement with ray. It means that the laws of refraction of light are obeyed. Our next diagram, this vertical line I draw is the normal. We shall still have the incident ray, the same incident ray at an angle I. That angle can be given any other letter. And we shall have the refracted ray grazing on the surface of the medium. We will still have a wick, implying that this angle is still I, but I is the same as R, only that we are saying that we are using I, since I is equal to R. Light is still moving from last A, and this is our second diagram. The point of incidence is still O. And finally, we will have the last diagram where we have the incident ray and the total internally reflected ray. I will be equal to I again. Remember, don't forget to put the arrow to distinguish your diagram from your lines from rays, or to make your purported lines as rays. In case 1, we can say that I is less than the critical angle. In case 2, our I is equal to the critical angle. And in case 3, our I is much greater than the critical angle. I'll put that where C is the critical angle. And in case 3 here, we have total internal reflection happening. Total internal reflection would happen in case C. In case C. Now, important to note in our discussion of today is that in diagram 1, a ray, if you want AO, will be incident at a small angle of incidence. I will simply summarize and say in A, the angle of incidence, which is I, is small, and light is traveling from glass to air. Take note that glass has a higher density than that of air. And summarily we say hence there is both reflection and refraction. That is in diagram A. There is both reflection and refraction. However, the refracted ray is very weak. In B, the angle of incidence is increased, much as it may not appear to be increased on the diagram. The angle of incidence is further increased. It is further increased, and the angle of refraction, which I have called R, also automatically increases. It also increases. Now, at a particular angle which we are calling the critical angle, particular angle of incidence, critical angle in bracket, which we are labeling as C, the refracted ray grazes the interference boundary. The refracted ray grazes the boundary, as you can see. In other words, it lies along the boundary, and this implies that the angle of refraction is 90. Refraction, which is R, is 90 degrees. That angle that we are talking about is called the critical angle. The critical angle. This is a very common question where they will ask you to define the critical angle. That angle is called the critical angle. Yeah, in case the video is not clear, you just ignore the video, take the audio. You are aware that I will be sending you the summary of the notes. I may not change the situation. The video sometimes is unclear because of the network of the area where I am. So that angle is called the critical angle, and we can define critical angle is the angle of incidence, of course, in the dense medium, in the more dense medium. It is the angle of incidence in the more dense medium, for which the corresponding angle of refraction is 90 degrees. The corresponding angle of refraction in the less dense medium is 90 degrees. Sometimes we can say that the critical angle is the angle of incidence in the more dense medium that gives the angle of refraction in a less dense medium as 90 degrees, or the angle of incidence in a more dense medium that causes the refracted ray to graze the boundary between the two media. Now this implies that as the angle of incidence, if we proceed to look at the next diagram in figure 6, incidence increases more or further, a point is reached where all the light is totally reflected, or incident light. A point is reached where all incident light is reflected and none is refracted at all. When this situation happens, we proudly say that we have obtained what we can call total internal refraction. When that happens, we say that we have obtained total internal reflection. Now the angle of incidence that is now much greater than the critical angle results into formation of total internal reflection. A brighter reflected ray, remember in the first two cases the reflected ray is weak, brighter reflected ray that is strong is observed in the in the more dense medium, and no refracted ray is seen in the less dense medium. Hence we say that total internal reflection has occurred. Total internal reflection occurs mainly as a result of two conditions. There are two conditions, but we can look at how can we define total internal reflection. I'll use TIR. Is said to occur when light incident from a more dense medium is reflected within the same medium where within the same medium with none refracted in the less dense medium. In other words, we say that all the incident light, that's why we say that all the incident light is totally internally reflected. However, there are conditions which we must note as candidates. There are two important conditions. One is that light, I'm using the word must, but you can say must travel or must be traveling from a more dense to a less dense medium. It must be moving from a more dense to a less dense medium. And if you're not using glass and air, as we have said, you could use water and air. If you're not using glass and air and you're not using water and air, you can use glass and water, because in either case, the first medium I'm mentioning is denser than the next medium. The second condition is that the angle of incidence, as you've seen, the angle of incidence in the more dense medium must be greater than the critical angle. In this case, we do not consider reversibility of light at all, because when we consider reversibility of light, it means the medium where light is coming from will now be a less dense to a more dense, and that will contradict with the first condition, and therefore total internal reflection cannot occur. The next important thing we need to look at is the relationship between the critical angle, between C, which is the critical angle, and the refractive index, which is using that symbol. This comes from our second diagram, that if we have and light does not bend unless it is being refracted. So the diagrams, if they must be used, they must all portray straight lines. Now, in order for us to derive the relationship, we shall consider glass and air. Glass has a refractive index which shall note as that, and air has a refractive index